I forget even how we chemistry time. Today we're talking about acids and bases. Today, is the mic on? Yep. Today we're talking about acids and bases. This is a fun topic. Lily, go turn the light on so that people can actually tell what's going on. Do it now. Welcome. Vice Chemist Lily is here to share the good news about chemistry, the proverbial, as it were, gospel of chemistry. You know that gospel means good news. And one of the good news of the chemistry is that there is no set definition of acids and bases. So usually, almost always, I would say, when I do something like this, which is lean against the board like this with the marker in my hand like this, I say, let's start out by defining this. But that's the first thing we're going to talk about, is that there is no set definition. There is no agreed upon unified definition, not because it would be impossible to have such a thing, but because in different situations we want to have different definitions. Let me try to think of a lay people's example. Here's a great lay people's example. It might be beneficial for me to have varying definitions of fruits and vegetables. I might want to say, I like vegetables on my pizza, and by that I mean peppers, onions, what else does people like on pizza of vegetable variety? Olives, of those things, sausage, yep, of those things, of the three things that are actually real that isn't what Ty said, of those three things, only one of them is botanically, that is biologically a vegetable. We define in biology, or at least in botany, we define a vegetable as a certain portion of a plant that is not its fruiting body. And we define a fruit as the fruiting body, the thing that carries the seeds hither and thither such that then they will sprout into a new plant. Of those I mentioned, onion would count as a vegetable. Really, vegetable, we don't even really define that in botany because it doesn't make any sense at all. It's pretty much, you could say it's defined as any part of the plant that is ingested that is not the fruiting body, whereas fruit is the fruiting body, and that makes sense, doesn't it? It grows little flowers, and the flowers have pollination, so that's what a flower's job is, and then that will grow a seed. And so if you let an onion fully grow, it will have flowers at the top. In fact, if you've had, this is not where we were going to go, but if you're, I would say grandma because my grandma does this, but if your grandma grows flowers, the flower called allium is actually a variety of onion or garlic. And that shoot with a little kind of, it looks like this. This is the ground. Here is the onion, which is a bulb, by the way. And it has these sprouts like this. You've seen green onions probably. And then if you let them grow, they will have this kind of like cloud of really pretty beautiful white or purple flowers. Interestingly, depending on the acidity or alkalinity of the soil, depending on the pH of the soil, these flowers will either be white or purple. So we did kind of bring it full circle, but that was an accident.
But not based on genetic variation at all?
Yeah, probably to some extent, but it at least partially has to do with the pH of the soil. All that to say, this we would consider botanically, such that to the extent that any such thing exists, this we would call a vegetable, whereas the pepper, and this is not a botany class, and I did not go to art school, but the pepper grows kind of like that. There are leaves. This is a decent drawing of a pepper. Please don't, if you have comments, you have to bring them in person. Comments are disabled for this video. But the little peppers, and you've seen peppers at the grocery store, or maybe you've grown peppers, but they grow with seeds in them, and that is considered a fruiting body. So really, that's a fruit. And so my pizza, when I say I like the vegetables on pizza, I'm using a different definition than if I were to say, here is how vegetable and fruit are defined in botany. So we have a sliding scale of definitions for fruit and vegetables not because we're all stupid and we can't agree. You know, Moses could come down from Mount Sinai and say, this is a vegetable, this is a fruit, no matter what. But it's actually advantageous to have these different definitions because in different circumstances, I want to talk about these different concepts in different ways. Same thing with acids and bases. Someone could, in this case not Moses, but we'll say, I was going to say Arrhenius. We could say Lavoisier could say, acids are defined like this always, bases are defined like this, but in different situations, we want to talk about different acids and bases. For instance, in biochemistry, many of the secretions of the human body we want to be able to consider those acidic or basic because of their reactions that take place within the body. But they don't meet the properties of what we consider acids and bases in the analytical or in the inorganic chemistry lab. They don't, for instance, not every base, especially in your body, things that we want to consider basics for the purposes of biochemistry, do not lend a hydroxide ion. Even the ammonia that you had in the lab, that doesn't necessarily lend a hydroxide ion. It's NH3. So we have different definitions of these, and let's go through them now. We have, first of all, turn the page. We have, first of all, the Arrhenius model. And is that pronounced Arrhenius? Sometimes I say Arrhenius, sometimes I say Arrhenius. I think he's Swedish, and Swedish is not a language I'm familiar enough with to say whether this should be pronounced with the hard H or not. So Arrhenius definition. And we're going to leave these pretty bare bones so that they're easier to memorize. You can obviously get more in-depth in this, however in-depth you want. It's pretty much all here. So the Arrhenius definition is probably the most basic. If I were to tell, which I do eventually, tell freshmen about this, I tell them this one. Acids, let's use the phrase donate, or the word donate. Hydrogen ions, bases, donate, hydroxide. And these are all conceptual frameworks. Even things that we would say, like this, potassium hydroxide, you can see how chemically this would donate a hydroxide ion, right? It would be in equilibrium with potassium ion and the hydroxide ion. That's pretty simple. But even this is more complicated. This is still just a conceptual framework, because what's really happening is this only happens in water. Both of these have to be, actually all of these have to be in aqueous solution. Well, ta-da! That's not anything. Both of those have to, all of the definitions of those have to be in aqueous solution, to my knowledge. Because water is physically separating. It's the negative end of the water is attracting the positive potassium ion, and the positive end of a different water molecule is attracting the negative hydroxide ion, physically tearing it apart. Even that is a conceptual framework. The way that you're envisioning that in your head is almost certainly wrong. It's happening in a much different way, but this is a functional conceptual framework. Like it works to think of it that way, so we do it. Next definition is the Bronsted-Lowry, and this one's sick because I'm going to do it in, I was going to say italics, cursive again. Bronsted. Why is this one so sick? Yeah, because we get to put a cool slash through that O. I think this person was also Swedish. Nope. Danish was Bronsted and English was Lowry. And in this definition, we talk about, this is why I was hesitant to use this verb donate in this one, but in this one we talk about hydrogen ion donors. That's an acid. And a base is not a hydroxide ion donor, it's just a hydrogen ion acceptor. And so you see, this widens up the field quite a lot, because some things will accept a hydrogen ion, but they would never donate a hydroxide ion. So now the definition of base has expanded here. The Bronsted-Lowry definition of a base, we could even say, is a looser definition than the Arrhenius definition. In Arrhenius, it has to donate this specific polyatomic ion. In the Bronsted-Lowry, it just has to be anything that accepts the hydrogen ion. And this is the time in your book when it talks about conjugate acids and bases, but let's not talk about that yet. Let's instead first talk about Lewis acids and bases. I'm going to put underlines under these so that we can tell which ones are which. And the Lewis, it opens both definitions up quite a lot more. An acid, in the Lewis definition, is an electron pair acceptor. And a base is an electron pair donor. I'm going to ensure that I got those in the right order, because I remember it as it's the opposite of what I think it should be, which is an unsafe way to remember things. You would ask. Hold on a second. I don't think so. Not usually. Also, I'm realizing now that the little feeling I've been having on my chin has been that interacting with the microphone. So the video probably sounds like. Hopefully it doesn't, but it may be the case. The captioner is going to have a hard time with this one. I like to assume that there's a person at YouTube who has to type out captions. I know that's not the case. But this is obviously a much wider definition because you know even from physical science, those of you who spent more than 9 cumulative hours in physical science, you know from physical science, in general, in chemistry, in Red Book, what almost always happens in a chemical reaction. Electrons mediate that. It all has to do with the electromagnetic force. There's almost always an exchange of electrons. And so this opens it up very widely. The Lewis acid is a very, very wide definition of acids and bases. Pretty much any time electrons are transferred, we consider one an acid and one a base. There are exceptions. There are reasons when that wouldn't happen. But these are the definitions basically from narrowest to broadest. The Arrhenius definition is the narrowest, and the Lewis definition is the broadest. In the examples given here in the book they have boron trifluoride combining with ammonia, becoming I truly do not know what you would call this thing. I guess boron fluorine nitro hydride. I don't like that. Apparently does exist, but in this case, the ammonia has donated electrons to the boron trifluoride, and so the ammonia is a Lewis base. It's also, by the way, a Bronsted-Lowry base. And the boron trifluoride is a Lewis acid, but it is not a Bronsted-Lowry acid because it can't, there's no look. No. And it certainly is not this because it isn't that. As far as I can tell, these two are the same. But the difference is in the bases for Bronsted-Lowry and Arrhenius. But this is neither a Bronsted-Lowry nor an Arrhenius acid, and this is not an Arrhenius base. It is a Bronsted-Lowry base, but they are both Lewis acid and Lewis base because of the electron transfer. Now let's talk about conjugate acids and bases. Let me erase my really, I think, delightful botany pictures, but no one was being nice about it. I thought Mr. Loverchuk was going to say, those are beautiful pictures, but no one did, and so that kind of hurt my feelings. But other than that, my pictures, though, could you say something nice, please? They were really good, okay.
So with the reaction, right, it's going to sound really dumb.
No.
But because there needs to be an exchange of electrons, okay? So that means that in a chemical reaction, there has to be an acceptor and a donor, correct?
I don't think I'd go that far. I'm trying to think of examples where that wouldn't be the case to, like, as a counterpoint. I can't right off the top of my head. I don't think that's strictly speaking true. There wouldn't have to be a transfer of electrons. There definitely would not have to be a transfer of electrons, because if you think of just this reaction, neither of them has given or taken anything. This is just two hydrogen atoms coming together to covalently bond into a diatomic hydrogen. There was no transfer of electrons. They're now sharing. What was this one's is now just both. They just share. So yeah, there wouldn't always have to be a transfer of electrons. I did say earlier that most of what we're dealing with is the movement of electrons. We're always talking about the electromagnetic force. And even in this case, when I was explaining that, I said they're now sharing electrons. So we're always dealing with electrons, but it's not always, strictly speaking, a transfer of electrons. Whereas this, I think, would have to be. I don't know. I mean, they are sharing them still in this one. This is the book's example. What was your actual question? Because that was just like the prelude.
Would a reaction have to have
An acid and a base. I don't think so. Let's look that up after a while. It's not, as far as I can tell, it's not mentioned in the text whether or not that's true. I don't think it goes into that much absolute. Like, it doesn't say all chemical reactions are Lewis acid and base reactions. I don't think that's true. And just saying that sounds bad. I don't think that's true. But we'll look it up to be more specific after a while. For now, let's talk about conjugate acids and bases. What does it mean for something to be conjugal or to conjugate something? You know? Like when you conjugate verbs when you're taking your Latin or Spanish, they're at the most basic, they're coming together, conjoined. Conjoined would be the adjective version of that. Or we talk mostly in English about conjugating verbs like I swam, he swam, she swam, we were swimming, those kind of things. That's verb conjugation. But conjoin would be conjoined is the adjective form. To conjoin would be like a verb form, but they have come together. So when we're talking about conjugal acids and bases, we're talking about almost like the reverse form of the acid itself. So if the acid is HCl, it has to be combined with water. By the way, what acid is, you should know how to name acids and bases. This is going to be really important. Hydrochloric acid plus water is in equilibrium with, actually for the strong acids, we usually just, and we're talking about strong and weak acids here in a second, but we usually just use becomes the hydronium ion plus the chloride ion. Talk about this guy real quick. Have you been introduced? Hydronium is H3O+. It's really another way of expressing H+, because you see that is the same as, right? You know basic math, so yeah, that would be, we'd add another H and we'd add a positive charge. And it's just really another way to express it. It does exist. H2O, H3O plus the hydronium. For bookkeeping reasons, we can treat it just as a hydrogen ion, because it always happens in water anyway, because we know that's the definition, at least of Arrhenius acid and bases, they have to be in aqueous solution. So we have here, let's say, what is this? What kind of thing? What species is this? Acid. This, then? Yeah, that acts as a base. This, then? Have you gotten this far in your reading yet? This is the conjugate acid. Oops, CON. And then this is the conjugate base. Let me read you the book's definition of the thing. A conjugate acid is a species produced when a base accepts a hydrogen ion. That would probably, I'm sure you have that written down because I checked your vocab. Did I check your vocab? Yes. Okay. A conjugate acid is a species produced when a base accepts a hydrogen ion. A conjugate base is the species that results when an acid donates a hydrogen ion. So we express this as it's in water. What has accepted the hydrogen ion becomes the conjugate acid. What has been removed, the hydrogen ion has been removed from it, is considered the conjugate base. Lowry interactions involve conjugate acid-base pairs. I should have said, forgot Bronsted. Bronsted-Lowry interactions involve conjugate acid-base pairs. A conjugate acid-base pair consists of two substances related to each other by donating and accepting of a single hydrogen ion. The acid is what will donate the hydrogen ion. The base is what will accept the hydrogen ion. Remember, we're using the Bronsted-Lowry definition here. The conjugate acid is what has accepted the hydrogen ion. And the conjugate base is what has donated the hydrogen ion. It's almost like verb conjugation, because we just went from future tense, what will donate and accept a hydrogen ion, to what has. Past participle? Which one is had swum? Is that past participle or is that past perfect?
I'm really bad with participles.
I think it's past perfect. And then this is just a definition, but we also talk about the idea of monoprotic and polyprotic. Mono and poly, meaning one and many. Protic is the adjective of proton. What's a proton? How do I express proton in chemistry? It's just that. That's a proton. This is just an proton. Just one. Because remember, hydrogen is a proton and electron. It's not spinning, it's teleporting. But a proton and one electron. That's hydrogen. There might be, if it's deuterium or tritium, there might be some neutrons thrown in there. But as far as charged particles, it is a proton and an electron. And so if it loses that electron and becomes H+, it's now just a proton. So a monoprotic acid would be like hydrochloric acid, one proton. A polyprotic acid would be like sulfuric acid, more than one hydrogen. That's it. Be careful though, because that's acetic acid, and while it has 4 hydrogens, only one can be donated. That's actually why we show it this way for acetic acid. The one out front can be donated. These ones are kind of stuck. They're part of this polyatomic ion. Remember, this whole thing, if you remember polyatomic ions, this whole thing is kind of bonded together covalently, but this one, this ionically attached hydrogen ion, can be removed. So this is still monoprotic, because we don't take them out of the polyatomic ion. You're looking at me a little confused, but does that make sense? Okay, you're not confused. You're just smiling. You're just happy. Just happy to be here. Strong acids and bases, and then we have 2 math things to do.
So, I really was not paying attention to that last part. I'm going to be honest with that. So, why can't the 3 limiter just stuck there?
Yeah, the 3 is part of the acetate polyatomic ion. This H3 is part of the acetate polyatomic ion. Polyatomic ions are themselves, it is an ion, but it's 2 or more atoms bonded together covalently. So these are covalently stuck. These 6 things, C2H3O2, 7 things, they can be separated, but in this case, they're not separated in water like the hydrochloric acid, where this H is removed and the chlorine they're separated by the water. That doesn't happen here. The H is removed, so it's monoprotic, but this just stays as acetate. I'm going to trust that you did your vocab, because many of these things we probably should talk about, but they're mostly vocab. So let's just talk about strong acids and bases, and then I thought there was Ka and Kb in here. There is. Okay, good. And then we'll do pH and pOH, which those are they're mathematically probably the most complicated thing we've done ever in chemistry, but they're still really basic, and they're conceptually a lot easier than some of the other things that we've done. Way fewer steps, and your calculator can handle the complicated math. But for now, we're going to talk first about, well, hopefully, strong acids and bases, and weak acids and bases. It does not mean, I'm not going to insult your intelligence by writing this down, but I'm going to say it. It does not mean these are very corrosive and these are not very corrosive. That's not what it means. These ones just ionize completely. For example, nitric acid. Oops, I was using that on my boogers. Now I feel like that's disgusting. No one better touch the whiteboard ever again. They ionize completely. This is totally separated by the water. Why would that be considered a strong acid? Why would we use the adjective strong for that? They're not connected anymore. They've been separated. So now think about it. For a certain amount, for let's say 1 mole, for 1 mole of this, now there is 1 mole of hydronium and 1 mole of nitrate. Okay? Whereas if we have this, both monoprotic, so we don't have to worry about that. But with this, we now have 1 mole of hydronium and 1 mole of nitrate ion. In this, we use this symbol in equilibrium with. This goes back and forth. And so now we start out with 1 mole of this. We will have less at any given time. It won't always be the same half that I've dissociated and the same half that have not. Each one is in equilibrium with. But at any given time, we'll say, and this is probably, we'll have to do the Ka to figure out how it would actually be, but half a mole of hydronium and half a mole of acetate, because the water has less affinity for those things, and so it makes it so that it's constantly going back and forth. It's always in equilibrium with. So this one does not fully ionize. So ionizes incompletely. At any given time, only part of it has ionized. You know what I mean by ionized, right? We talked about that in physical science, but let me just remind you. Ionized means the water has broken this thing up into its constituent ions. We might express it as H plus NO3 minus, but since we're already talking about the water, we'll just put the water in there too. The strong acids are hydrochloric, hydroiodic, perchloric, nitric, sulfuric. I'm getting this from a table on page 645. You don't have to write them down. Hydrofluoric. Oh, sorry, that starts the weak acids. So just, God bless you, just those 5. I think I said perchloric. I think it is just those 5. There are, FYI, there are more corrosive acids than these. There are some very strong, what are called superacids, that will generate a much lower pH, even into the negative pHs, even when they're not saturated or concentrated. But these ones are the ones that ionize completely. Let's talk real quick. You might have to end up, because Ty's already packing up, you might have to end up doing pH and POH on your own. It is, as I said, pretty simple mathematically. I don't think you'll have a problem with it if we don't get to it. But let's talk about the Ka and Kb. You remember KEQ. KEQ equals what? The rate constant K times the concentration of the products over the concentration of the reactants. Raised to whatever power the coefficients were, right? We should probably put, that's fine for now. I was going to change it to say sum of the products, as we do have to add them together, but this is fine. So that's KEQ. Ka is just the same thing, except now, why would I draw an E? Don't draw an E, draw a K. Ka is that for an acid. So what are we going to, if we look at this equation, what are we going to end up with on our acids for KEQ? We're just doing the same exact thing, but look at, let's say we're doing KEQ, I've just changed the EQ to an A, we're doing it for this acid dissociation. H3O. So first K times the concentration of H3O times the concentration of NO3, right? And I think that's balanced, so I don't think we need to worry about the coefficients. Over, the only tricky part, what's it over? Yep. Why? Why not water? No, because water is liquid. Remember, we exclude that just like we did for the KEQs. We exclude the pure substance. So it's the same thing as KEQ. We're just now using it for the reaction. And the reason that this is slightly different, it's the same thing for KB. Oh, we forgot to talk about strong bases and weak bases, but it's the same thing. Strong bases ionize completely, weak bases don't. The strong bases are all the group 1A metal hydroxides and calcium and barium. I pointed at the wrong dang thing. So lithium, sodium, potassium, rubidium, and cesium hydroxide, and calcium and barium hydroxide. Why not strontium? I don't know. Also not lithium. I lied. Lithium is not on there. So just sodium down hydroxides, and then calcium and barium. Those are the strong bases, hydroxides. And then for KB, let's say we had, let's do a weak one. So let's say we have, well, I just said lithium hydroxide. Here's our equation. kind of. This is a little bit. Sorry, forgive me. That should be this. I'm running out of room. Does that add up? Oh, it just doesn't include the water. The book just doesn't ever include the water, which is fine. It's fine because we don't need to worry about how that there we go. Even if we didn't include the water in this one, what we'd end up with is this, right? And remember, that would change this down here. These two things are the same as H3O+. So it doesn't matter if we choose to write it this way just in dissociation form, or if we choose to write it in combination with water form, doesn't matter. And that's the same for this. So your book has just written it this way for the base. So once again, K times, in this case, the concentration of lithium times the concentration of hydroxide over the concentration of lithium hydroxide. Let's make a prettier bracket. Higher values of Kb then would mean what? A water acid or base. Higher Ka or Kb, looking at the way the math works out, higher Ka and Kb means it's shifted towards the right, which means it's a stronger or weaker acid or base. If this value were higher, assuming the same K, same temperature and pressure and conditions. Stronger, yeah. Higher Kb means a stronger acid or base. Good. So as a very basic review, these are the same as KEQ, they're just for acids and bases. And then that leads us into, which we don't have time for, but that leads us right into, real quick, we can probably, you can stay one extra minute, because this really is fairly simple. Same thing, but now we do it for water. Which this is just a kind of like a little thought experiment. We don't actually do Kw. Kw for water is K, except for water is this. Always dissociating into these two things. That makes sense. It actually ends up being 2H2. But now we get concentration of hydronium, which we sometimes express as just the hydrogen ion concentration times the hydroxide ion concentration over the concentration of water, which we actually leave out, so it's just 1. So, and this, for all intents and purposes, is just that. So the Kw is just the concentration of hydrogen ions times the concentration of hydroxide ions. And if we want to find what's called pH or POH, it's just the power or potency or potential, any of those things could be the P of hydroxide or hydrogen, depending on what else is in it, what else is mixed in. And it's pretty simple to calculate. Both of those are just equal to negative log, at least make it pretty, last little bit, negative log of the concentration of whatever you have there, hydroxide or hydrogen for pH, hydroxide for POH. And this is where it all comes together. These two are, you wouldn't say inverse, they add up to 14. For a given substance, pH and POH add to 14. So if the pH of our hydrochloric acid was 1, say, the POH is 13. And these are negative log because the concentrations are exponents. Remember, logarithms are the inverse operation of exponents, and so the concentrations 10 to the 14th. The log of that is pH is 14. Does that make sense? Oh, sorry, it's negative log. So 10 to the negative 14th would be pH 14, which means very, very little. So that's why it's a base. And negative log of pH 10 to the negative first, much bigger concentration, means pH 1. And now you see why you can sometimes have negative pHs. Because if we had 10 to the second, the negative log of that would be negative 2 pH. Is it okay just because it's 333, or is it actually okay?